Senhoras e senhores, bom dia. É com grande satisfação que a Universidade Estadual de Campinas recebe a todos para o primeiro workshop internacional Alvenaria Estrutural em Situação de Incêndio, avaliação do estado da arte para desenvolvimento de normatização nacional. Sejam todos bem-vindos. O workshop é organizado pela Unicamp e UFSCar, que é a Universidade Federal de São Carlos, em parceria com a Abece, Associação Brasileira de Engenharia e Consultoria Estrutural, ANICER, Associação Nacional da Indústria Cerâmica, e Bloco Brasil, Associação Brasileira da Indústria de Blocos de Concreto. Este workshop tem os objetivos de divulgar os conhecimentos técnicos atuais de projeto de alvenaria estrutural em situação de incêndio, com foco na segurança estrutural e normatização nacional, apresentar a abertura dos trabalhos da Comissão de Estudos para a elaboração da primeira norma técnica brasileira de alvenaria estrutural em situação de incêndio. A Unicamp caracteriza-se pela pesquisa de alta qualidade e sua produção científica é certamente relevante. Diante desta produção, a Unicamp também se caracteriza pela contribuição às normas técnicas que asseguram a qualidade dos projetos de engenharia civil, fornecendo dados de materiais estruturais típicos do Brasil. A Unicamp também se caracteriza pelo grande número de patentes, o que demonstra a capacidade de transformar conhecimento novo em desenvolvimento tecnológico. A aproximação da indústria de materiais de construção civil com a Unicamp poderá alavancar a inovação de forma a gerar novos produtos com qualidade necessária para assegurar o bom desempenho dos edifícios de alvenaria estrutural em situações excepcionais, como o incêndio, e garantir uma vida útil mínima de 50 anos, atendendo às demandas mundiais de sustentabilidade. Nós agradecemos a presença de empresários, autoridades, professores, funcionários e alunos da Unicamp. Nesse momento, convidamos para compor a mesa de abertura professora doutora Marina Sangói de Oliveira Ilha, diretora da Faculdade de Engenharia Civil, Arquitetura e Urbanismo da Unicamp. Convidamos também o professor Dr. Armando Lopes Moreno Júnior, professor associado do Departamento de Estruturas da Faculdade de Engenharia Civil, Arquitetura e Urbanismo da Unicamp. Professora doutora Carla Neves Costa, professora do Departamento de Estruturas da Faculdade de Engenharia Civil, Arquitetura e Urbanismo da Unicamp. Professor Dr. Guilherme Ares Parsequian, professor associado do Programa de Pós-Graduação em Estruturas e Construção Civil da Universidade Federal de São Carlos. Engenheiro Aurélio Fortes da Silva, vice-presidente de Tecnologia e Qualidade da Abece. Senhor Sandro Roberto da Silveira, diretor de Relações Institucionais da ANICER, presidente da ACEVIR e coordenador do CB179 ABNT, Comitê Brasileiro de Cerâmica Vermelha. Senhor Carlos Alberto Touil, arquiteto, consultor técnico representando a Bloco Brasil. Nós, nesse momento, convidamos para fazer uso da palavra a professora doutora Marina Sangói de Oliveira Ilha.
Bom dia a todos. Gostaria de cumprimentar inicialmente os que compõem a mesa. É uma grande satisfação, em nome da Faculdade de Engenharia Civil, Arquitetura e Urbanismo da Unicamp, dar as boas-vindas a todos nesse importante evento que temos hoje aqui, né? Que tem como pano de fundo o desenvolvimento da normalização nacional e também o estado da arte, né? Discutirmos aí os avanços no conhecimento nessa área. A vida moderna ela incorpora materiais e componentes nos edifícios, o que necessariamente acaba por contribuir com um maior risco de incêndios. Então, é muito importante que a gente trabalhe não só com a prevenção e o combate, mas também em formas de mitigar os impactos quando da ocorrência de sinistros. Não termos normalização nacional tem um peso muito grande, então é uma satisfação, sabemos dessa iniciativa. Utilizar normas de outros países, ainda que metodologias de cálculo sejam similares, faz com que nós tenhamos que adaptar muitas situações, né, dado que temos materiais e componentes diferenciados. Então, desenvolver os procedimentos e os cálculos em âmbito nacional com as características de materiais que aqui temos é de suma importância. O uso de manuais técnicos, apostilas, né, toda uma documentação técnica tem o seu valor, só que não tem o peso de uma norma que, em última análise, além de traçar os limites de segurança, né, tem como função também proteger o usuário final, né? E serve de referência para os códigos de proteção ao consumidor, né? Então, é de suma importância termos essa iniciativa aqui hoje. Já há alguns anos, a Faculdade de Engenharia Civil, Arquitetura e Urbanismo possui pesquisas nessa área, então é uma consequência natural e uma grande honra para nós sediar esse evento que acontece hoje. Em nome do professor Armando e da professora Carla, eu parabenizo pela iniciativa, extensiva a todos os envolvidos aí na organização desse evento, e desejo aí que hoje e amanhã sejam dias muito produtivos na temática em estudo. Muito obrigada.
Nós agradecemos aos componentes dessa mesa de abertura. Nesse momento, essa mesa se desfaz. Convidamos seus membros a se dirigirem à plateia para acompanharmos os trabalhos do dia.
Pessoal, inicialmente, obrigado pela participação de todos. Em nome da comissão organizadora, agradeço muito a presença de todos vocês. Esse é o primeiro passo na busca aí de um caminho muito grande em termos de normatização da alvenaria estrutural em situação de incêndio. Gostaria de agradecer muito ao professor Guilherme, professora Carla e todos os nossos apoiadores, que sem eles praticamente não teríamos esse evento. Alguns avisos. Existiu aí, está existindo uma confusão em relação ao local do evento. Por isso que teve esse atraso logo no início. A partir das 5 horas, a reunião de norma ela será no auditório da Faculdade de Engenharia Civil, Arquitetura e Urbanismo. O auditório não é aqui é o auditório do Centro de Convenções. A Faculdade de Engenharia Civil, existe o endereço desse auditório da Faculdade de Engenharia Civil. Então, só para que não haja mais confusões, a reunião de norma, após as 5 horas, será no auditório da Engenharia Civil e o minicurso será também no mesmo auditório da Faculdade de Engenharia Civil. Eu convido, então, o professor Guilherme Parsequian para que ele faça parte da presidência, seja o presidente dessa primeira parte do nosso evento.
Okay. Obrigado, Armando. Bom, então, obrigado a presença de todos, as várias parcerias. Vamos dar início, então, ao nosso workshop propriamente dito, e a gente começa com a apresentação do Dr. Ali Nadja. Dr. Ali é da Universidade de Ulster, na Irlanda do Norte, e é um dos grandes pesquisadores nessa área. Ele é especialista em estruturas em geral, não só estruturas, mas construções em situação de incêndio, não só a construção, mas também o comportamento do incêndio, vários aspectos. Ele é bem especialista nesse tema. Hoje ele vai falar para a gente sobre alvenaria estrutural em situação de incêndio, contando um pouquinho aspectos gerais e do Eurocode. So, Dr. Ali, thank you very much for coming here, and I'd like to invite you for your lecture, and it's up to you.
Thank you. Good morning, everybody. First of all, I would like a few words. I would like to thank all the organizers who made this happen here in Brazil. And also I would like to thank Ferguson, who's been in touch with me in the couple of months. Also, I would like to thank the people who take care of me, Angela and Louis. And I had wonderful days here before I start my talking here in this place. It is my first time here in Brazil and first time in South America. My presentation today, I'm going to show you about research, performance, and design, mainly in masonry walls. So you can see this is the building. Oops. This is the laboratory, which I built in Northern Ireland. And it is 6 million, which grant from the government. And I built a state-of-the-art laboratory, which we can test nanoparticle, physics, chemistry, and also structure up to 2-3-story building inside that building. Okay. If I start with the introductions, okay, buildings are the center of our social, economic activities. Not only we do spend most of our lives in building, but we also spend most of our money in building. The built environment is not only the largest industrial sector economic terms, it is also the largest in terms of resources flow. So most money goes in the built environment. If we come to the fire are recognized as one of the major threats of life and property in many countries. The primary goal of fire protection is to preserve life safety, because life safety is very important. And it's a priority. A second goal is to protect the property, safeguard the environment. Property, business, running business, activities, and safeguard the environment in order to make it healthy and, of course, important for the generation coming over. If we take the fire itself, it's a young discipline, rapidly emerging field, because the fire can cause a lot of damage and can sort of way change the policy of the government. Broad and disciplinary, because it comes from the physics, chemistry, engineering application, and address complex problems. because you're talking about heat, you're talking about flame, and also you're talking about how the fire spread as well. The other thing you can spot just at the bottom here, the economic impact of fire in building has been estimated of 1% of GDP, a vast sum now exceeding 10 billion a year. If you compare the earthquakes and the flooding, and you compare the fire, you can see that the fire is causing more damage compared to the others, and more investment and more protection has to go to the building and health and fire safety. I think you are aware about this, and we are all aware about this. So it happened just recently. It's incalculable loss of 200 years old age. The Museum of Rio institution gutted by the fire. It is a nice building, but there are so many questions. Why made the fire to happen? And how the fire, where exactly started? What was the ignition? And of course, how it is spread from one block to another block. So in sort of way, the fire was localized, but couldn't sort of way constrained by the fire resistance doors, windows, and roof, and of course spread it all over the building. It is not only the place where fires strike. Something happened before 2005, but there are so many buildings. I'm just bringing that for you, because 2005, that was the bid for the Olympic Games. And because of the strategy which happened in Madrid, 3 days people couldn't travel under the underground and sort of paralyzed the city. So if this happened during the Olympic Games, we'll have empty stadiums. So in that case, the bid was won by China. So you can see fire can change the views of the organizer of a big event, and of course it has an impact on the economy as well. If we come to the regulation, I think this is a fire happened in London in 1666. It is funny to see the 6 3 times here. So you can see the regulation started to ignore things and take action on something else. So you can see in 1212, Dutch banned in London following the Great Fire. The Dutch, it's like in the roof they put what you call dry leaves or dry branches in order to make the roof. And this has been banned because the fire can strike any time and can spread from one house to another house. So the new regulation had means of enforcement by the employment of surveyors in 1667 and required building to be built of bricks and stone. So you can see the decision here, long time ago, they know one of the material who can stop fire to spread is the stone and the bricks. So they decided early time, this is the main material which can sort of save lives. No Dutch roofs behind parapets, and recessed wooden windows from 1774. So you can see to produce a document or a code, it takes some time and not straightforward. Legal liabilities. Regulatory, reform, fire safety, order, responsible person, fire risk assessment of general fire precautions, competent person, enforcement by fire authority, problems. What about our qualification? What about our skill? What about our competency? Evaluation. So there are so many questions here we could ask what happened in these two buildings, or maybe the previous building as well. As we said, in In the 1667, the British government decided that masonry and stones will be the main element to be used in construction. So masonry material has been successful, used for the construction of fire-resisting elements since the need of fire protection became apparent. Just an example here. We know what happened in Grenfell Tower. And we know how the fire spread so quickly. And we know that the combustible material used in the facade is flammable, and of course, the fire can spread so quickly. But in this particular facade, the fire cannot spread because it's masonry, and masonry is not flammable. So it's sort of protection. So it is a protection apparent compared to new material used and old material used. This is the new one, this is the old one. And you can see if fire occurs somewhere in any compartment, I don't see the fire will spread from floor to floor, except if you don't have some clothes, in the balcony. The role of masonry is in a compartment. It divides blocks to another block. And of course, has been engineered to act as a fire barrier. So fire may be striking one room, it cannot move to the other room because it has the barriers of the masonry. And serving to compartmentalize the fire, to constrain the fire, and not the fire to spread. And of course, what you can see, this is what we can see in dwelling, and this is what we can see in hospitals. So you can see the different fire loads as well. Role of masonry walls, fire separating walls are commonly employed in a variety of construction situations, from domestic dwelling to large commercial building. So you can see library, and you can see commercial, what you call center. And you can see the fire loads. The fire load is different from one to one, and could be here over 100 megawatt. And previously it could be maybe 3 megawatts. So the fire load changed from compartment to compartment. And of course, every wall is subjected to different heating compared to another compartment, depending on the fire load which is available in the compartment. So the fire load can be fast, which can be library, shopping center, and so on, and can be ultra fast, chemical plants, and could be mediums, and could be slow. So masonry can be subjected to one of these three scenarios. And of course, we have to make sure that the type of masonry chosen for plants is not the same as for transportation or dwelling. So it is what you say, a special treatment and special work in order to make sure that the safety of the constraint of the fire cannot spread from one place to another place. The masonry also can sustain the heat from one side to another side. Let's say the early ignition and before the flashover, this is the main concern point where evacuation can take place and people can sort of evacuate the building, and masonry can be one of the safeguards to maintain the evacuation of people. And of course, beyond that, masonry can help the fire authority and fire brigade to interfere or intervene during the firing compartment. But there is one thing else, the cooling is another factor. And of course, you could have a problem in the cooling, but not problem in the heating. There is a lot of secret here, which can be developed compared to what we do in the heating. If we look at the constructions, building regulation, this is what it's about. Every building should be designed and constructed so as to inhibit the spread of fire, to stop the spread of fire, provide adequate resistance, and of course to the spread fire and smoke, and of course of different uses in building by compartment walls. So every compartment with different fire loading in a different building has to be treated completely different than the other one. And all the compartmentations which has walls has to be designed properly to that fire load. Maintain the stability of the building. This is very important. It's related to the integrity. And provide adequate resistance of the spread of fire over the roof of one building, and this is what happened in Rio, to another, having regards to the position of the building. In other words, every building shall be designed and constructed so as to provide adequate resistance to spread of fire and smoke, because smoke can kill before the fire gets to the person. And of course, at the end of the day, is to maintain the stability of the building. This is what happened in Grenfell Tower. Over 80 people died. And this is what happened in Rio. It's a chaos in society. So failing to do so in regulation, you could have another Grenfell Tower or another Rio somewhere, and of course multi-millions pound losses of stacks up annually, not to mention the losses of human life. This can be repeated in another place if we don't follow the regulation properly. In fire situation, masonry walls are usually subjected to severe heating or severe heating on the exposed face, giving rise to thermal gradients through the thickness of the wall. This is just recently what happened in Belfast, where I live. You can see it's a commercial building. It's closed. It's like what you call Primark. It's like C&A or Mark & Spencer or Debenhams. So it's all closed inside. So if it's closed, it's open compartment. And if there is a fire, the fire can spread so quickly. And of course, it's what you call a fast speed fire. It doesn't give even the timing, what you call for the evacuation. Luckily, the fire spread in the roof. But it could be better controlled. But the fire spreaded after the roof to floor until to the last floor. And that should not happen. Because one of the main reasons, they were doing some work, refurbishment, construction. So they are expanding the building. And so many mess could be during the construction and fire sort of way if they find the fire load, the oxygen, and of course the heat can travel so quickly. And that's the problem which happened in Belfast. It's a big loss. It's an iconic building. And the problem now, they close all the city center part of it. So the business sort of way is a big loss. Not to add that to this building, but to the neighborhood building as well. There is an investigation in this building, and hopefully it will be decided after my return in Belfast, and the discussion will be on the 8th of November. We know about the type of masonry. They are sort of solid, cellular, and hollow. This is the relation to blocks, but are so many others in relation to clay. When you say about masonry fire situation, if the wall is unrestrained, this leads to different thermal expansion of the material, which in turn induce thermal bowing towards the fire. With the hot face of the wall expanding more rapidly than the cooler one, the wall will tend to bow towards the fire, and that's what we see. Remember, when we test a bearing wall, it has to be free on the two sides. But when you test a non-bearing wall, it has to be restrained all over the sides. And of course, we expect a non-bearing wall restrained all over all sides could withstand more fire resistance compared to the load-bearing one. If we talk about the free bowing, okay, because it can affect sort of way the stability of the building or the stability of the wall itself. You got the hot, and you got the cold from the other side. So the heat travels by radiation, and next comes the conduction. So in the simplest way, because you're talking about Boeing, that the temperature here could be before the mechanical is affected by the heat. So you can consider, a simple equation that the temperature is almost linear, but in reality it is not linear. So what we can come with the simple beam deflection and a cantilever beam deflection. And that could be our wall standing, restrained top and bottom, and restrained and free to move from the top, where there is a gap, sort of way. When it is restrained bowing, okay, the wall tries to expand, and it has some restraint coming from the top. And of course, you can see here, wall at certain time cannot be non-bearing wall. It becomes bearing with certain loading coming exerted as what you see internal forces here. So you'll have sort of the Euler formula equation. So this is an engineering concept here. And the stresses comes with pi squared E divided by the slenderness. So the slenderness is one of the main factors for design wall. And of course, using this concept of engineering, we can come with some equations here that for deflection for wall with gap and no gap. And of course, you can include the effect of the load restraint, which is part of the mechanical because you got the Young modulus involved, and you could have the effect of the mechanical at early stage before it becomes very hot on the exposed face. Remember, we are talking just bowing before it becomes very serious when the fire goes to a certain high temperature, let's say 600, 700, which is the flashover. What we can see here is something what we call about the stress strain. Every unit of masonry produce stress strain compared different than the other. So this is the complexity in understanding the masonry units inside the wall. So you can see different one, but the thing we can sort of get is the level of stress and strain is almost stable in the masonry compared to the steel and compared to the concrete. So we can see that the masonry can be an element stable during the fire compared to a column and compared to the beam. So if a column fail or a beam fail, so masonry sort of if it's non-bearing, it will become bearing. And therefore, we have to be very careful when we design a compartment when there is non-bearing masonry. Because fire can sort of change the way of load will be distributed. Here, if I look at the reduction factor and in the thermal properties from different material used in the what we call in the masonry, we can see there is still not enough information produced in this particular area. So it needs more knowledge and more work in this particular area. If I come to the thermal properties, the Annex D informative, and the Pro EN 199612-2003 provides the thermal properties of thermal elongation, heat conductivity, and the specific heat capacity, and the density at elevated temperature for some types of masonry. But what we can sort of extract here, the density is the most important parameters. So the density sort of control the sort of design which can be applicable in the different material used in the masonry wall. So the most significant material properties, as I said, characterizing the fire performance of masonry is the density rather than the type of bricks, as the density is a measure of the porosity of the brick which will govern the thermal properties of masonry at elevated temperature. And this is from a friend of mine, Perkins, 1996, who is a retired professor from Aston University in England. When we come to the fire safety in building, this is what we teach our engineers. There are two things they have to know. There is something called prescriptive approach or based approach, which states how a building is to be constructed. And something else called performance-based approach. And that states how building is to perform under states criteria. So you can see here, states how building to be constructed, and here status of building is to perform under state criteria. So you have to challenge some other things not existing in the prescriptive approach, which is mainly based on the experimental testing. So let's discover what they call about the prescriptive approach. Set of rules for prescriptive approach, for example, minimum fire resistance for members. So you have to give a minimum of fire resistance for a member. Maximize fire compartment size, this is very important. Maximum travel distance, and minimum number of exits. Etc. All this, it is available in the document B, and that's what we call the legislatives. What we call the fire strategy of any building can be found in one document. And this document B is used in England and Wales, and document C is used in Scotland, and document E is used in Northern Ireland. So you can see different states, different regions. They do have their own document, but very close to each other. But remember, there is north of Ireland and there is south of Ireland. But the south, they use the document B as well. So you can see the strategy is very, very important to have a document, a unique document, and this unique document is used by all the consultants who works in fire, and even the fire authority as well. And of course, the building control. So an example for prescriptive approach. So it is given in the document itself about offices, shops, commercial. It gives you sort of the height of the building and what could be the minimum fire resistance on that particular element. So any element and that sort of way the fire resistance is below that is not accepted if it's equal or 18 meter in sort of way offices. If it's 30, 40, so it's not accepted. So 60 and above, that will be accepted. So this is the sort of table or prescriptive approach. And how they did do it, how they did that, okay? There is a standard fire. And that standard fire, you can see it's a logarithm. It's an increase of temperature, but with no what we call cooling in sort of way. So they don't consider the geometry, they don't consider the ventilation, and of course, it's pure fire resistance in the furnace control. So to achieve the above requirement, the construction works must be designed and built in such a way that in the event of an outbreak of fire, you design an element, you test it, and you take in a compartment. That compartment, it could be a cinema, it could be theaters, so the fire load is different. And you have to check that element can sustain the period of time in that compartment. So this is what is the secret in that. However, that particular element, sometimes, you design it for 60 minutes. And the fire could take longer beyond 60 minutes. And this could happen, the same thing, this is what happened in Belfast. So the curve is what you call the fire resistance, is exceeded during the fire itself. And of course, you expect some failure of the element and cause the fire to spread or travel in sort of way. Standard fire resistance, the basic requirement formulated for masonry structure in the case fire include something called load-bearing capacity, integrity, and insulation. So this is a load, has to be placed on the wall and has to be maintained stable during a period of time, during a heat of, let's say, 30 minutes, 60 minutes and over. The integrity should not be any cracks to let the flame to cross the wall and spread on the other side of the compartment. And insulation is more or less the same, but the fire can spread from one side to another side through the heat and not through the flame. So there are two things here we need to consider. In practice, this function connected with fire resistance of specific structural element. And you know that the wall itself is a structural element. It could be non-bearing wall and it could be a bearing wall, because I said during a fire, the non-bearing wall could take some loading and becomes a bearing wall as well. So in the case of fire, the analysis of structure may be conducted on the level of isolated element. This is how you test it, and how you take it in compartmentation with simple model in 2D subframe, or you take it in a global analysis with better view, I would say a better performance, how fire spread from compartment to another compartment. The history of the fire resistance is coming from a furnace, and it is from the 1800 or the late 1800, and you can see that has been established for structural fire behaviors. 1917 US standard started, 1932 UK started, 1933 US produced another document, slightly the same as the British one, and the ISO came after that in 1995. And ISO is like a curve used by all over the world. And 2003 is the EN came over, and the difference between the EN and the what you call the UK one, UK is calibrated by thermocouples inside the furnace, and the EN is calibrated by thermoplate. That's the difference between the two. But the curve, it is the same. When we come to the prescriptive approach and the performance approach, we can see the steps which the engineers must do when the wall exists in a compartment. Design of building, national fire regulation, that's what you have to understand. And next come to the fire safety requirement and 5 test element if it's required. And of course, you can use what you call data, information from the test in order to make sure that your element can be sustain a fire for a duration 60 minutes, 90 minutes, and so on, depending on the need of the compartment inside the building. The performance approach, we can see is there is some similarity. So they used the regulation as well and the fire safety requirement, but they do some calculation and they do some structural temperatures and model, and of course, advanced one. And some tests can be useful to implement it in the model, to have more parameters and different criteria, and analyze the whole structures, or part of the structure, or the structural element. So there is some similarity, but there is more challenge in this. The major steps of the fire design of any element inside the compartment, considering non-bearing and non-bearing and bearing walls in a compartmentation, is the fire behaviors, the thermal response where the heat is sort of way accumulated in the wall to stop the heat to travel, which is the insulation, and integrity, the flame, to travel from the other side. And next comes the mechanical effect, because there is some deterioration of the load, or mainly on the what we call the standing wall, because you'll have part of it disintegrated and you'll finish with the what we call effective thickness rather than the full thickness. The fire behaviors can start with nominal fire curve. And this nominal fire curve, this is what we call the normal standard real fire scenarios. So you take consideration the ignition and the flashover and the cooling as well. And the nominal standard fire curve for the furnace, you can see, is not considering the evacuation timing ignition, and you can see the flashover can be more or less the same, and it can be only heating with no cooling, as you can see, because the fire load can be sort of way finishing at certain time. The nominal standard can be different from building to building, depending on the fire load. It can be hydrocarbon fire, where car parking, sometimes. It can be an external fire curve. This is also a car parking happen, but it can be open one, can be closer one, or industrial plantation. And this is what we use for the building construction. It has a limitation, not based on real fire data. Test repeatability is difficult, and especially in masonry. No cooling phase, uniform heating, uses gas temperature, not fair. And as I said here, it's uniform temperature, but in the real fire scenario, if the fire starts somewhere in the corner, you cannot have the same heat all over the area. But widely used, can be useful for crudely comparing product. We know that the standard fire curve started so many years ago. We're still using it over 100. So do we have to keep it or do we have to change it? So there is a lot of talking about that. So the nominal fire curve, you know what it's about. There is something came in Europe, it's called parametric fire curve. This parametric fire curve is combining the real fire scenario and the standard fire scenario. And you can see this is the standard fire curve and plus the cooling as well. So there is sort of what you call combinations has been implemented to understand the cooling stage in the real fire scenario, which is not considered in the previous scenario, which is the nominal fire curve. This can be very useful. Assumption in parametric fire curve, no heat build-up in the pre-flashover phase of fire, which is the same as the standard fire. Temperature uniform in the compartment, uniform heat transfer coefficient in compartment boundaries, and all combustion take place in the compartment. The what we call the limits of parametric fire curve, the calculation exists in the Annex A, EN 199112. The size of the compartment, you can see it's limited to 500 meters square. The openings are in the walls and not in the roofs. Maximum height you can use is 4 meters. The fire load density you can use up to 50 to 1,000 megajoule per meter square. You're talking about 3 to 5 to 70 kilograms of timber per meter square area, which is cellulosic type of fire load. So you can see it has some limitation, but still a lot of work to do in compartmentation. We can see that it considers the fire load and also the opening, the geometry of the compartment, and the thermal properties of the lining walling element. You do have the density, the specific heat, and the thermal conductivity. This is basically what wall is needed in the compartment, depending on the density, specific heat, and the thermal conductivity. This is the main parameter for all researchers working in masonry walls, bearing or non-bearing. The burning and cooling part of the curve is taken in consideration. Okay, burning phase, and of course the cooling phase can be done in this parametric fire curve. which is quite useful, but very limited in the size of the compartment. And that's very important in relation to the opening, because the opening sort of way can make two things. Can make the fire control by the opening, which is the ventilation, and can make the fire control by the load. There are two things. If it's by ventilation, the fire can be severe fire, and you can have the flashover. However, if it's controlled by the fire load, the fire could be slow because the compartment is so big. Let's say it could be an airport where the ceiling is sometimes 5 meter, 10 meter, 15 meter. So you're not expecting the flashover to happen. And that's what we say localized fire. So we have to understand the fire, how becomes localized, and next how to spread and travel and becomes engulfed. So we know we use what you call the curve, which is mainly using the extreme fire. But we're not using how the fire spread or start and next travel and becomes engulfed. We're not using that. Eurocode is not considering that. There is a lack of information in that. And I will come to that at the end. Now, we can see that the influence of the opening factor. If you take a different opening factor, you can see the load, what you call the duration of the fire, is different from an opening to another opening. So this particular opening can make a big difference how the fire behave in the compartment and how the fire behave and sort of ways constrained by the wall inside that compartment. The other influence is the density. We know the density of the wall in the Eurocode, maybe in any other code, it has an influence on the behavior of the wall. And you can see that the density from 1 to 1, from 200 to 1,000 can make a big difference. So we have to understand and take all the parameters all together and study very carefully in compartmentation and the heat in the compartmentation due to the geometry, due to what you call the opening, due to the fire load, and of course, take that in consideration before we make our wall inside that building. You can see here the boundary condition, which we talked about. This boundary condition usually goes to the wall, okay? It can be bearing and non-bearing as well, which has the density and of course specific heat and the thermal conductivity. This is the main parameters which goes to the boundary all over this compartment. It goes to the ceiling, it goes to the ground, and it goes to the wall. Sometimes the weakness can be in the ceiling and the fire can travel through the cavity to the other side, and possibly this is what happened in the Rio, but I don't have enough information on that particular building. There is something else called zone model. And zone model, I don't see maybe is used in my discussion with some of you in this place. The zone models is sophisticated energy balance model and assume uniform temperature in each zone, normally computed based, several commercial codes available, example, the ozone and the CFAX. CFAX is mainly related to smoke movement, and the ozone is mainly related to the heat, to the boundary of your compartment. Similar drawbacks and benefits to parametric curve. The ozone is used nowadays in Europe a lot and is being developed, and I will come to that point. As I spoke to Perkison, I completed a book about the ozone model and also how fire is controlled by localized fire. And I will explain what I mean by localized fire. There is something in the Eurocode, but they never considered an element vertical in related to the, what you call the localized fire. It's open with no vertical element. That vertical element can be a column itself or can be a wall itself, but the fire can be in a distance or inside it. And this is not considered in the Eurocode. And nowadays, it is considered after a big work, a project in Europe with my partner, and we came with the solution of that. And I make sure that I will send to Perkison the legislatives, the new one, which I created for all Ireland, plus the book. And of course, the consultant can make a better design of offices, and of course, a better design of industrial plantation. And you'll see there is so many examples which can be used, even with the ozone itself. Coming to the fire behaviors in the zone models, as we came and I spoke about that, is a balance between the mass balance and the energy balance. Am I okay with time? Okay. The next is another challenge could be the CFD. Okay? CFD, yes, it could be useful, but if you do have the right heat release rate, because the fire load produces heat, and it's measured by heat release rate depending on the smoke coming and the oxygen. So that smoke and that oxygen is an element to be implemented in the CFD in order to understand how the smoke sort of way travel and accumulated, and how the heat sort of way travel from another part to part. So the heat release rate is the most secret way in order to create a good model using the CFD. If you don't have the heat release rate, it will be very, very difficult. It's like a lottery. You can be on the right way, or you can be in the wrong way. So CFD modeling is a computational fluid dynamics. Can predict huge range of phenomena, but difficult to use due to many uncertainties in input variables. That's what I said about the carbons or monoxide coming from that particular fire of the load which is under fire, and the oxygen inside the compartment itself. And still more, what we call a research method in this area. So we can conclude about the performance-based approach. We must continue to promote the performance-based approach, otherwise we'll rely on luck, simple as that. The procedures for the determining fire load capacity of masonry walls according to the Eurocode. So we've seen how the design behaviors inside the building from the prescriptive approach and from the performance-based approach. And let's see what in the code itself is saying about. So behavior of masonry wall in high temperature is conditioned by what we call various factors. The masonry unit material, because there are so many of it, and different from country to country. And the type of masonry unit itself could be solid, hollowed, and the thickness is one of the main factors in that particular type of masonry. The mortar, it's another element which can make a difference in the unit altogether, especially for lightweight. And ratio of design load. So the loading ratio is an element to be considered for load-bearing walls, and every load ratio has got a different time of fire resistance. This is the main parameters. The thickness, eccentricity, sort of way, because you do have an effective thickness at certain time working when it's load-bearing and can cause an eccentricity loading. And the density is an important element for the behaviors of the masonry wall. Type of wall structures could be single leaf, cavity, load-bearing, no load-bearing. When you go to the Eurocode, you need to be careful what table you have to use. It's not one single table can be applicable for one particular, what you call load-bearing wall. Every particular what you call table is designed to specific load bearing and no load bearing. It could be separation, it could be non-separation. You have to use the proper table. They look the same, but they're not the same. So you need to be very careful what sort of table you can use. I know it's a bit confused sometimes, because you'll see there is some two, what you call numbers available in the table. Due to this fact, while applying any calculation method for masonry walls fire resistance, it is necessary to operate with temperature-dependent properties that should be determined separately, not only for each masonry material, but also for each type of masonry unit. And I think Perkison is working in that, and I wish him luck for this, but he has to make the advantages, limited, otherwise it will be difficult in sort of way. The tabulated data for determining the fire resistance of masonry wall is available in Appendix B, EN 199612. The table gives a minimum thickness of wall necessarily to achieve the requirement fire resistance. So it is a minimum thickness available in the tabulated section. For specific types of wall and for determined way of loading, you have to be very careful which table you have to use here. And that's the meaning of it. And you can see for category 1, okay, you do have the ceramic, you do have the silicate, and normal weight concrete and others. You got the alpha, which is the ratio between the design loading in fire and design loading in what you call cold one, before fire taken in consideration. You'll see that the values in between, because it's a protocol of test, you could be sitting between these two values. Let's say if your alpha is less or equal 1, if your alpha, which is the load ratio, is less than 0.6 or equal, you can use, let's say if you're sitting at 140, okay, if your thickness is 140, and you can see 140 here, 140 here, 140 here, and that's it, if you are using this. But what you can see here, something between bracket. This is mainly that your wall has got what you call finishing material from the two sides. Let's say the 10 millimeter from the two sides gave you 90. But you can see here they finish more or less the same, what you call fire resistance for load bearing. And that's how it is, what you call the protocol of test brought this fire resistance. You can see thinner with finishing could be the same as a thicker with no finishing. And that's how the procedure of testing. But when you consider the tabulated one, you have to consider with no finishing, and you can consider basically this line. You can see the category is for lightweight concrete, cellular concrete, and of course cellular concrete depending on the density. The calculation method for masonry walls for fire resistance in EN 12, there are included two calculation methods for fire resistance, what you call resistance determinations, simplified given in Appendix C, advanced in Appendix D. In UK, they don't accept this simplified method. They believe in the tabulated section. Advanced, as I said, there is some, depending on the parameters, how to create a better understanding of fire in the, when you use finite element model. But the simplified method, it goes step by step, as we call it. Determine temperature profile across the section, evaluate the reduced cross-section, which is function of the thickness, effective, calculate the capacity, reduce cross-section, verify of this capacity is not less than is required for appropriate combination of actions. And all these values is available in the simplified approach, and there is a table for that. Okay, so you got the fire situation. The ultimate limit state should satisfy the conditions. And you see that the slenderness and the what you call the area, and of course, which is function of the thickness per meters, and of course, or per millimeters, and of course you got the strength, which is important to be considered for that. And the different temperatures, I have to go a little bit quicker here because I don't have time to respect for the other speakers. So you do have a table here to get the values of the distribution temperature from one side to another side. And of course, when the temperature increases, it will affect the strength. And therefore, the strength has to be taken in consideration of this temperature on that particular time. Of course, the eccentricity is affected due to the thickness which is working at certain time, is not all of it, and there is an effective thickness which is considered, and you can calculate it and check if it's in the limit boundary in order to make sure that it can sustain by the loading applied on the top of the wall. So there is a table which you can have your values, theta 1, theta 2, depending on the values of what the material used for this particular wall. Okay, and the temperature distribution you can see is non-linear rather than in